me share my screen. Where- Okay, so after we kind of talked about those different data harmonization methods or data scaling methods, so that way you can compare data across different, like from different laboratories and stuff. We want to create a toy data set where we can test out some of those methodologies and see. And so the first thing I want to talk about is, are you guys familiar with long and wide format? I know Nicole and I have talked about it before. So in statistics, there's two types of main ways that you can format your data that you can then do your analysis on. And they're called long and wide, depending on how you have it set up. And so here we have a wide format. And so here we have our city. And so here are 3 towns that I picked randomly from here in Utah. So we have Provo, Salt Lake, and St. George. And I just made up some number of abnormal cases. I know we don't get nearly that many here in Utah, but just making them up. And so here, so for 2018 in Provo, this is how many, 2019, 2020. And this type of format is great for kind of visualizing time data because you can look at a specific row and then see trends that are going across as time increases or decreases. But the problem is that most statistical analysis software, like whether using R or Python's scikit statistics or whatever you're using, you're not going to, it doesn't like this format. There is an exception. I'm pretty sure ANOVA, so if you're doing an ANOVA analysis, you are going to want it in a wide format. So then our next format is this long format right here. And so here we're going to be repeating the data over and over again. So each column, so the way I do it is I break it down onto what variables are you actually looking at. So here we're looking at the city, the year, and the number of abnormal data points. And so we have to have 3 different columns for that. And so here we have Provo, and 2018, 2019, and 2020 are going to get their own row. And then we put the number of abnormal results that came up on each row. Then we do the same thing with Salt Lake and St. George. 95% of the time, you're going to want it in this long format. And it makes it easier too when we use libraries like pandas and stuff to pull out specific data as well. So if we wanted to pull out all the Salt Lake data, it's super easy to do that in pandas. It makes it harder if you're trying to pull that data out with long data. But long format is super easy, or we could go through and just select all the 2018 data, vice versa. So that's the format that you should be using most of the time when you're creating data sets. Now that we got that out of the way, let's look up some of the data sets that I kind of found online in preparation for this. So let me pull up a new. And a link in that for each one. So the first things that I did was I looked up normal values for everything, and I found two different laboratories that posted what normal values should be like, and we're going to want to know those. And so the first one was the Benioff Children's Hospital, and I'll put the link in. I can actually spell today. Hospital. Plasma. No. So here, down below, for each of the amino acids, they give normal ranges for each of these. Put that in the chat. And so we're going to be using those values. I printed some of these off so I don't have to keep a million screens open. The second one is the Mayo Clinic. And they have a... And these are just used for general guidelines for kind of roughly what we're going to need. And so this one's super nice because they have it listed out by age as well and what those values should be. So, and it's nice for some of these, they give the ranges for them as well. And so let me put that in the chat. The next one, oh, I guess there's one more. I almost forgot about this one. It's the LabCorp. Plasma amino acid reference. And so they have these, they also left out the values and the ranges that they use. So one of the first things we're probably going to want to do is compare all the normal ranges across with each other and see how they differ across the labs. Put that in there. And then the next thing and then I looked up a couple papers that listed their data that I thought we can recreate using kind of the hacker statistics we talked about last time. So the first one is the amino acid reference intervals by high plasma samples. So this is a sample. They give their references for children in Brazil. And one of these tables has them listed in here. So it's table 5. So they have the concentrations in there. And obviously these data sets aren't going to be perfect because they're looking at populations that have disorders and stuff in them. But I figured it's probably close enough for what we're using it for. And the reason I like this one was because it does give a standard deviation for the values as well. So that way we can put that into our formula. Put that in. So that's part of the data we're going to be looking at. The other one I found was for an alternative method where they did plasma-free amino acid analysis. So I thought that would be interesting to kind of get those. But I think this is for an older population that they used. Let me look at the mean age. The majority of the patients were between 40 and 60. So it's not completely ideal, but I figured it would be good. Let me pull it up. Yeah, so here's the paper talking about that. Let's pull it up. And part of the reason I use these two is because they're free. The government does not pay for, or at least the state government doesn't pay for journal subscriptions. So, and the table we're going to be using for this one is we're going to be looking at table 2. This one doesn't give the standard deviations, but I figured we can probably infer that maybe from one of the other papers or from the reference laboratories. Yeah, I think that was the only one. The table we're going to steal data from to do that. And then the last one.
Oh, did we get the link for that one, Bryce?
Oh, whoops. Nope, you didn't. And I'll still keep my eyes open for some other ones as well. While we do this, that might be better suited. Okay. This is the last paper we're gonna recreate data for. This one, these are obviously patients with Alzheimer's. And so we want the HS that we want to seal the data for, and those are healthy subjects. And so we're going to be stealing from this column right here for these. So yeah, those are the data sets we're going to be working with, or at least stealing the data and recreating what a hypothetical data set would look like based on those. Okay, so the first one we want to do is we want to make a table of all the different laboratories reference values and see if how well they align with each other. And so I know everybody, depending on who you talk to, there's different ways to do this. I personally prefer using Excel to enter in data. I just find it's easier to visualize and type it in because you have to type it in anyways using code. So if you have to type it in, just do it. The only problem with doing it that way is you have to be careful of spaces. So if you write something and there's a space at the end, that space is now part of the string. And so you need to just be careful not to do that. Okay, So let's take a look at this first one, the Benioff. I don't know if that I'm saying it correctly. Children's Hospital. And let's put in all these values. So looking at this, what do you guys think? How should we set up our data format for this, based upon what I talked about before? Here, and I can put that back in.
So if we're going with the long data set, right?
Yep.
It looks like we're gonna have two repeating categories. Well, maybe not. Maybe four. Well, no, you could do it like you have in your table where you have adult and children, and then go by age, right? As your second column.
Okay. So we'll just say age as the second. Okay.
Yeah. Yeah, because I guess you don't need children or adult age will take care of it. And then so these are the normal values for each disorder.
Yeah. So well, for the amino acids that are being picked up.
Right.
On there. Yeah, and I want to go back through. I'm trying to meet with our director to see if I can get what some of the cutoffs are for a lot of these, and
Mm-hmm.
and so that way I can be like, oh, this is what is like what would be considered for secondary testing, and then figure out the z-score for that, and then do some algebra to figure out what values there should be based on these.
Gotcha.
So
So because we don't know the cutoffs, could we just do a column of lower limit and upper limit?
yeah, I don't like using spaces, so I just do underscore. And technically, I probably shouldn't be doing capitals with these. That's kind of bad practice. So, I guess this kind of goes back to variables. So there's two different ways that most people do this. So this is called snake case, where I put an underscore in between them. There's another way you could do this called camel case. So we say like this. So where there's the space would be, you would just make it a capital letter. So I prefer snake case. So, okay. So we have our age, lower limit, upper limit. We should probably put right here what lab this came from. And let's do standard deviation right here. All right, anything else that you think we should include?
So you're going to combine all of them right now on this one?
Yeah, so I'll get rid of this top stuff.
Oh, okay.
Yeah.
Well, yeah. Well, and then I guess the amino acid, right?
Yep. Yeah, and let's actually move all these over one. Yeah, I have a tendency to capitalize things way more than I actually should. I don't know why, but my fingers are always like, capitalize the middle N of that word, or stuff like that. And I'm always having to go back and through. I don't know how I developed that habit. So, all right, so we have amino acid, lower limit, upper limit, standard deviation. Okay. It's good with these two to make sure that you don't have any empty space. So like don't write notes off to the side right here or anything. because if you put something right here, when we load it up into pandas, it's going to think that's its own separate column. And so we're going to have to pull it out. It's very annoying. So don't do it. Try not to leave anything blank in between here. If we don't have a value for something, just put NA and call it good. And so there's a feature in pandas, if we want to remove all the features that have NA in it, you can do it. But if you just leave them blank, it takes a little bit more work. So, all right, let's go back to here. Okay, so the first one we have is, oh, go ahead.
Bryce, sorry, I want to double check. With pandas, can't you fill all missing values with NA? Isn't there a way to fill null?
Yeah, you can.
Okay, I just want to make sure I remembered that, right?
Yep, no, yeah, that's what I was saying. There's extra steps involved if you decide not to do it. So, and I think they even have functions that take in empty, like you can specify that there's empty spots as well, but I just find it's good practice to just put it in there. So that way you know it didn't accidentally, like someone didn't forget to put it in there or something else like that. Like they're like, this is a very deliberate, there is no value for that. So here we go, capitalizing things again. Okay, so we have alanine. So we'll say this is child. We don't know. We'll specify, I don't know. We'll figure it out when we get to the other ones. They don't provide a standard deviation for this, so that's okay. I don't think with any of these lab ones they do, but we'll just put it there in case they do. All right, so then we're going to do the same thing. We're going to say alanoff, alanine, benioff. We'll say adult. Wow, that is not what I was hoping for. Wonder why it did one of these in Calibri and the other one. Not that the color matters. When we save this as a CSV, it'll get rid of all that other metadata that's associated with it. We'll wait to do benioff and just copy these. So we'll say NA, NA, NA. I'll fix all that stuff later. So, child 8, 37, 15, 41. And in some regards, doing this might have actually been, since we're visually going to be looking at this, this might have been a good justification for a wide format, and just have, because if we were going to do this wide format, we'd have the lab, or no, we'd have the amino acid, and then we'll have each lab. And then we could have compared each of the values for those. So, but this works too. This way we can visualize it in pandas if we wanted to. Let's just do a bunch of these. And I think we could just drag it down with Excel, but it's okay. 4, 20, 13, 64. Yeah, I think there is about 40 or 50 of these. It's traditionally what they have. This one looks like 20 or 30-ish. So 6, 0, 6. And if we don't finish this up, I'll finish it up later and then send it to you guys. So that way we have it, since we're doing this in real time. And for some of these, if we don't have like the other labs, if they're all the same with these, then we'll just get rid of them. So like with the carnosine, but then we'll get rid of it if all of them don't have it, because then that's just pointless data that's just taking up space. So yeah, and I'll send you guys the wide version too, so you kind of can see the benefits of one versus the other for certain tasks and why you would want to use them as well for our next analysis. So I think I'm going to have to leave here in just a little bit to go to my next meeting. So we'll just keep going through this at a snail's pace until we get it. Yeah, and maybe if you guys wanted to do that too, if you have time, just practice doing the two different formats and then seeing what you can glean from each as well.
Should we divide and conquer? Since you have like 5 data sets, we could each take 1 or 2.
Yeah, if you wanted to. So I was just gonna, once we get this data all set out first, it'll be really easy just to copy and paste these. And so these first one's gonna take the longest. And then after that, it goes fairly quick. So I will not be. Yeah, it's very annoying when with some of these data sets that I get where they are missing values for things, because then I don't know exactly what's going on with it. And that's another thing you have to be careful of too, that we'll have to look at to make sure that that all the values make sense as well. So if we go through here and we are doing the analysis and we look and we see that the values here are like between 68 and 120 for 2 of the labs, but on the 3rd lab, it's like 99 to 180. We would have to think about if maybe that was entered in wrong or if that was just the lab is using a different technique, we'll have to do some further exploration of what's going on as well. And that one will be easier to detect using the wide format. So yeah, I'll let you guys go. But we will. I'll probably get this. I'll probably finish. I'll do all the analysis stuff because I have to. I want to get this done before a meeting I have coming up. So that way I can put some slides on what I found with the toy data. But we can still work at it as if I was still doing this all from scratch. So.
Yeah, I'd be curious because I have some questions about how you're going to do the analysis.
Yeah. Yeah, because my main thing is I want to see if we can suss it out. Because one of the things I want to do is I want to find out exactly how they do this, and we need to compare how they process it and everything else to see because one of the things that we need to find out is if we can compare between methodologies. And so that's part of the reason I picked some weird random ones was because it used slightly different methodologies. But yeah, it'll be. Oops, let's do that. But yeah, we can go through that and we'll just work at it one step at a time. So. Okay. All right. We'll see you guys later. So.
Bye.
Bye.